Okay, thank you very much. So this is a project with Natalie Cox at Princeton and Ricardo Fonseca, who's here and in a hammock in Brazil. And this has been terribly depressing throughout the pandemic to watch his good fortune. But I'm sure that in a couple of years I will be in contact about hiring Ricardo when he's on the job market. So this project is about peer preferences, and they're both theory and evidence, and I'm going to talk about the theoretical part today. Okay. So I think this should come as a surprise to not too many people that centralized college admissions, college admissions has really taken off, and something like a quarter of the countries in the world have a centralized system of college admissions at this point. And what this paper is about at a high level is about this famous quote by the statistician George Box: all models are wrong, but some are useful. And I really wanted to show this picture because I think it's just fantastic. And so the question that we're really asking, again, at a high level is, how useful are matching mechanisms that are constructed based on incorrect models? Okay. So to fill in the details a little bit, in school choice settings, we often like stability or justified envy-freeness. Okay. And to find these, probably most people on this call, right? The way that we do it is we sit down and we write down some preferences on some assumptions on preferences, and we then look at Galen Shapley's deferred acceptance algorithm and change it around a little bit to match our setting, and then we prove a theorem that says, if we use this mechanism, we'll deliver a stable matching under the assumption of preferences that we started with. Right? And so the more particular question we're asking in this paper is, what happens if this mechanism is misspecified? Right? The assumption we wrote down is wrong, in that students have preferences not only over the programs they attend, but also over who their classmates are. Okay, so they care about the ability of their peers. But the mechanism is just a standard one that only asks for preferences over programs. So I don't think this should be too shocking of a question. One, because there are hundreds of papers, literally, in the education and economics of education literature talking about peer effects. Okay. None of the countries, as far as I know, that I showed the graph of above, explicitly designed for peer preferences. And third, Catalini yesterday was saying this is a big problem that we don't know how to deal with. Okay, so at least in this room also there's some notion that this is something that we should be worried about. So just to touch on literature very, very quickly, there's some recent literature, empirical literature, talking about how indeed peer preferences may be the biggest part of preferences, right? So once we control for peers, students don't really care about anything else, or rather their parents in high school settings. Other people have talked about stable matchings with peer preferences before. So I know Marek is, I think I see him on the call, and he's done some work on this. We're going to be looking at continuum matching models today that I'll talk about, which is really based on, built off of the models of Azevedo and Leshno and Leshno himself. So just to contextualize what I'm going to be talking about. Okay. So we're going to have a continuum of students and a finite number of schools. Okay, where the students care not only about where they go, but also who they're, the ability of the peers they're assigned to. Okay. So let me get some punchlines before jumping in to the model. So the first question is, does a stable matching exist? If a stable matching doesn't exist, then we would have to do something to try to identify what we want. Luckily, a stable matching is going to exist under very mild conditions, but it's not going to be easy to find using existing mechanisms, right? So basically what it's going to be is, well, this is not surprising. If you care about students and peers, and you're only asked about your students, about your preferences over program, excuse me, then you're not able to express your full preferences, right? So we would need to elicit functional form preferences over not only the programs but over the peers, and we don't seem to have the ability or the will to do that. So the second says, all right, well, if we can't find a stable matching using existing mechanisms, what if we try anyway? Okay, so this is what we think of as kind of the situation that's being done currently, and we'll show that this actually induces a sort of tâtonnement process. Okay, where students' beliefs over their peers are going to be changing over time, and this may or may not lead to a stable matching. And we identify some sufficient conditions which lead to a stable matching over time. And the third is that is there a better way to match students to programs in this setting? And indeed, we proposed a more centralized process that looks like iterative deferred acceptance mechanisms that are used in some countries around the world. Okay. One thing I meant to put on the slide is that there is an empirical component of this paper. We're not going to look at it, where we try to identify peer preferences. But just to give you a scope of the problem, we conservatively estimate that something like 20% of people would have a different match, a different partner, if we just kind of subtracted their peer preferences away. Okay, so it's not a small problem. There's a large scope for redesign here. Okay, so if there are no questions, let me jump into the model. So there will be a continuum of students. This big theta is a type space, and little theta will be a generic student type. Eta is a non-atomic measure over the student types, and we'll just normalize the number of students to being 1. Okay. And there are a finite set of programs, 1 through n. Each of them has positive capacity, and there's also this program C0, which is just the outside option of programs that can take of students that can take any number of students, right? So C0 is just the option of being unmatched. Okay. Now, I think normally in a matching paper at this point, I would say here are what preferences look like. But the kind of like technical difficulty here is that preferences depend on the peers, and the peers, defining the peers. Well, I have to say what a matching is. So first we need to define matching, even in order to define the preferences, right? So this is a standard definition. A matching is a function that takes students in schools, right? It matches students into to one program. Sorry for saying program in school, I mean the same thing. Programs are assigned to some subset of students such that their capacity isn't violated. And the assignments are 2 ways. So if a student is matched to a program, the program is matched to the student. Okay, and so this is just in the notation that I set up before, but there are no surprises here. Okay, so now that we have our pretty standard definition of matching, now we're able to talk about student preferences. Okay, so each student is going to have a type, and the type is going to be made up of 2 components. It's this R theta and U theta. Can you see my mouse? Yeah, okay. So R theta is just going to be a vector of student scores at the different schools, right? So it's just going to be, we can think of these as the preferences of the programs over the student, where there's so it's an n+1 dimensional vector, 1 for each of the programs. Right? Nothing too exciting about that. Then there's the utility function of the student. Okay. And we'll use this notation here, this U super theta C given mu. And this is going to represent student theta's utility from attending program C given matching mu, right? So given where all the other students are going, this is the utility that C gets from, that theta gets from attending C. And I'll use this standard squiggly notation to talk about the ordinal preferences that are induced by this U. So the important takeaway here is just, okay, of course, schools have preferences over students. That's kind of encapsulated in R. Students have preferences that take as an argument the matching, where everyone else is assigned. And so we'll assume here, some relatively weak assumptions, and there are a couple of other small technical things in the paper. The first one is just that the scores and preferences are strict, right? So we don't have a positive measure of students who are indifferent between schools at different matchings, and we don't have a positive measure of students who have different who have the exact same score vector. Okay, it's just a richness condition. Okay. The second thing that we're going to talk about is what students have preferences over. So we're going to assume that students have preferences over the quote unquote ability of their peers. Okay, so this is different from maybe the couples problem that has been studied in the matching literature. We're going to assume that students care about the entire distribution of peer ability. So it's not just one person that they care about. Okay, and we'll capture that with this lambda function. Okay, and lambda is really, we can think of it almost like a CDF. It's the distribution of quote unquote abilities at each program. Okay, so what this says is for each n+1 dimensional score vector, okay, lambda tells you how many students are matched to school C at matching mu, okay, who have scores where the score vector lies below this exogenous score vector X. Okay, so we're tying the abilities here into the preferences of the programs, although it's easy enough to just kind of think of this as we can vary this in a number of ways, but the key point here is just that this lambda really captures the distribution, right? It tells you how many students are below some ability threshold. Okay. And we're going to assume that the student preferences depend. I write depend only on lambda of mu. They depend on the school, but in terms of the peer component, right? It's only on the ability of the students. Okay. So once you know the kind of full distribution of abilities, you don't care which particular student it is who's matched to the program. You just care about the full distribution. Okay.
Got it.
Yes.
So do I prefer to match with better students, or is there some resource division then, and I prefer to match with better students?
So Alex, you actually saved me, because I made a note this morning that I should say it at this precise spot, but it's very early and I forgot. I'm sorry. Thank you for the question. We make no kind of functional form assumptions on this. It could be that students like to be matched to programs with better students. It could be that students prefer to be matched to programs with worse students. It could be that they prefer to be matched at programs with more students, right? So we don't put any functional forms on. So in the paper, we actually we try to find the functional form of this in the Australian college admissions market, and I'll talk a little bit about the functional form of that later. But you know, anything goes so far, subject to these regularity conditions. Okay. So now we can define stability, which is almost completely standard at this point now that you know, with this definition, which is just that a student program pair is going to block a matching if the student prefers program C to her current assignment, and either that program hasn't filled all of its seats, or it has filled all of its seats, but it's assigned, it has a student assigned to it that has a lower score at that program. Okay, so the idea is that the program can just kick out that student and take student data. Okay, so the only non-standard thing is that now, of course, the preference that determines whether the student wants to block has a mu in it. Okay, so we have to keep track of how the preferences change potentially depending on the matching that we're starting. Okay. And so a matching stable if we don't have any student program blocking pairs. So I said I wasn't going to talk too much about existence, but let me just say a brief word that indeed we have existence. Okay, so if the peer preferences are in some sense continuous, as the matching changes a little bit, not that many people change their ordinal preferences. There's going to exist a stable matching. Okay. Now you know, just to talk a little bit about how we find this. You know, normally we can think of stability as a fixed point problem, right? So starting with this Roth and Van de Watte in like 1991, you know, some intuition is we start with the matching, we satisfy some blocking pairs, hopefully we get closer to stable matching and we continue in this way. Here we have to keep track of something else, right? If we were to do a procedure like that, which we do have a constructive proof in the paper. We start with a matching. In some sense, we satisfy some blocking pairs, but then we have to say, okay, now everyone's preferences may have changed because we've changed the matching. All right, and so the set of peers at each program are different, and so we're trying to hit a moving goalpost basically, but we're able to do. But we might have multiple stable matchings, and in the paper we talk about some conditions for uniqueness. But the takeaway here, I think, is that there exists a stable matching, and so we have something to aim for that's not controversial. Now, if I had shown the proof, I think a natural question at this point would be, great, so are we done? Because it's a constructive proof, so there's some algorithm for finding a stable matching. But the problem is one of complexity. Okay, so the algorithm, not surprisingly, requires the full functional form of student preferences. And I don't know how to elicit this in theory. I certainly don't know how to elicit this in practice. And there's some recent kind of like bounded rationality / market design literature that says, it may actually be quite difficult to do this both on the student side and on the clearinghouse side as well. Okay. And so the alternative, I think, is what's commonly used, kind of informally. I don't know if it's used actually to specifically about this problem, or if it just seems like a good idea. But it's something like deferred acceptance with transparency. Okay. So what do I mean by that? Here's an example of our empirical setting, which is college admissions in Australia, which uses a centralized clearinghouse, uses deferred acceptance. But students are very explicitly told information about the ability distribution from the previous year. Okay, so here is kind of just a sample of what the students are shown. They're shown the course code. Let's not worry about what this means. They're basically shown something that looks like the median, and they're saying, oh, this is something like the median score was 70 last year. Okay, and it's very explicit that it's last year. Now, there are analogs of this in many countries. So forgive me, I know this is a primarily European audience, but in the US, there's this famous publication, the US News and World Report, which publishes information about each program from the previous year. Okay, so there's some notion of learning from the past. Okay, so this is the transparency I'm talking about, just information on the past. So let's go ahead and think about this. Okay, so we're going to run just vanilla deferred acceptance, but we have some information for what the peers looked like last year. Okay, so let's just embed the framework that I talked about before into a discrete time model. At every time, we have the same measure over the student type. So we have a replica economy, and each student cohort is going to observe the matching from the previous period. Okay, and the initial matching is just going to be exogenous. And we're going to construct each cohort's matching using deferred acceptance. Okay. Now, students
Bobby, you have 5 minutes.
I have 5 minutes. Okay. So students have some information from the past, and we're going to assume. Let me not talk about why this is, but it seems to be empirically justified both. Well, it seems to be justified both empirically and from a kind of bounded rationality point of view, is that let's assume that the students believe that what they saw last year is going to reflect what they see this year, and so they report their preferences, quote unquote, truthfully, given the peer distribution from the previous year. And this is going to create a sort of tâtonnement process. We call this the TIM process, where basically the distribution of student types last year is going to play the role of prices. So I think this year is going to look like last year. I submit my preferences. I might be wrong. That's going to lead to a different matching and a different ability distribution that the next cohort has to affect. And our intuition from grad micro is something like, look, if we have this tâtonnement process and we have something that looks like prices, that if these quote unquote prices converge, we're going to get to equilibrium. And that's indeed what we find. Okay, so If the ability distribution over time converges, if it reaches steady state, that's if and only if we found a stable match. Okay, and we can make all these statements approximate. I think I've given some intuition, but let me not go into it too much and get to the central question, because I'm running out of time, which is, does this process converge? So let me give an example where the answer is going to be no. Okay, simple example. There's one program. There are Q students. Okay, and students are going to care about the mean score of student that's enrolled. Okay, so this S is just going to be the mean of the score distribution. Okay, students receive 0 utility from the outside option of being unmatched. If they're matched, they receive this utility V theta. V theta is just some intrinsic preference, which is drawn uniform 0, 1, minus this function here, which says, if I'm above the mean, I don't care about what the mean is. If I'm below the mean, I pay some cost K. Okay, where K is just some constant. Okay, so it's very much what we call big fish preferences. I don't care if I'm better than the average, but I don't like to be below the average. Okay. We'll initialize the matching where remember we picked the initial matching arbitrarily, such that the mean score is less than 1 minus Q, the number of seats available. Okay, so here it is. On the x-axis we have the score distribution. On the y-axis we have the share of students enrolling in this program of a particular score. Now in the first period, right, the students say, okay, the mean is actually quite low. All the students who have quality above 1 minus Q say, great, I don't suffer any peer cost because they're above the mean, remember. And they all have some random utility from attending, which is positive, so they're all going to show up. Okay, we run out of seats, and so we have, like Juan was talking about a couple talks ago, we're going to have a threshold where everyone above this is submitted. Okay, and that's going to be equal to 1 minus Q. What happens in the second period? Well, now the mean that the students see is actually up here, okay, because it's the mean of this green block. So now all of the students who are kind of matched, or all the student types who would have been matched in the first period but are below the mean, they now suffer this peer cost. And this peer cost might disincentivize some of them from showing up, right? And so in the second period, we're going to have a matching that looks like this. Not all of these students show up. Only 1 minus K fraction of students are going to show up. And so we're going to have this long tail. Okay. This induces a mean that is, again, below 1 minus Q. But then we're cycling, right? Because if the mean is below 1 minus Q, all the students above 1 minus Q say, great, I'm not going to suffer a peer cost, let me show up. And matching 3 is going to look just like matching 1, and we're going to cycle such that odd periods look like this and even periods look like this. Okay, so we never converge. By the previous theorem, we don't get to a stable match.
Bobby, can you wrap up in 1 minute?
Yes, I'll wrap up in 1 minute. And so, so let me not talk about the problem, but it looks like it's a problem of not getting to gross substitutes. We don't have something like gross substitutes in this situation. But let me say, just wrapping up, let me do the exact same example, but instead of the mean, the students care about the median. Okay, we claim that this generates a stable matching for all periods after period 1. So period 1 looks exactly the same. The first block of students shows up, right? Entering period 2, the matching looks exactly the same because some of the students who are below the median don't show up. But now what happens? Well, the median in period 2 is the same. The long left tail doesn't drag down the median, it's going to be constant, okay? Unlike the mean where the students drag it down, and so we're stuck here, okay? And this is indeed the stable match. So, so I just want to point out that the specific functional forms matter. We identify some sufficient conditions in the paper, which are based on the Australian market. They look like this, and this is the type of preferences that we identify, where there's kind of this ordinal ranking of preferences, and they have these big fish preferences. So we have this theorem. Let me, actually 15 seconds, Alex, sorry. When the preferences look like this, we're guaranteed to converge in finite time. And let me end on this graph. which says we're plotting the age of the program on the x-axis, and in the y-axis we're showing kind of the absolute value change of the median in the previous year. Convergence would assume convergence would imply this goes to 0, and we're seeing something like that. Okay, so we are indeed, according to our theorem 2, converging to a stable matching. Now we identify other markets in the paper that actually don't converge to a stable matching, and so the punchline is, you know, getting back to the question, how useful are matching mechanisms that are constructed based on wrong markets? We actually might fail to do well in some sorts of markets, not others. We show in some sense that students who are kind of at the low end of the ability distribution are the ones who are really negatively affected by this sort of thing. Happy to talk about the mechanism that we designed that we think does better. So thank you very much.
Thank you, Bobby.